Let's start our discussion of chemistry by talking about the early concepts, the early ideas that later formed into the early models of the atom. The idea of the atom first started with the ancient Greeks, particularly with a philosopher by the name of Democritus. He was born around 460 BC, lived for almost 100 years. Now, he reasoned that every object had to be made of indivisible particles, which he called atoms. Now, think of this. If an object was truly solid, if it was just one lump of matter, then it probably would not be able to bend. It would not be very malleable. It would be very rigid and couldn't move. Democritus said that in order for things to move, it had to be made of atoms, indivisible particles that can move around each other. You can picture this as if you take a handful of sand off of the beach, you hold it, it's very malleable, it moves, it flows, not because it's a liquid, but because it's made of little particles of sand. Same idea that Democritus had, we have to be made of atoms so that we can flow and move around and not be a rigid structure. However, his idea was argued against quite a bit, particularly by the great philosophers Plato and Aristotle, who were phenomenal philosophers and had a huge role in science. But they debated and said that matter is continuous, it's solid, and you can actually take that matter and cut it and keep cutting and cutting, so on. Basically, any object is like a block of Play-Doh, which you can cut in half, cut the Play-Doh in half again, cut the Play-Doh in half again, and you can do that infinitely. So Democritus' idea of atoms was kind of lost and not thought of again for over 2,000 years. It was reintroduced in the early 1800s by a scientist named John Dalton. He did this to help explain chemical reactions. Now here's what John Dalton's atomic theory summarized. He stated that all matter was made of indivisible atoms for many of the same reasons that Democritus reasoned that. But here are a couple other ideas that he threw in there. Every element is made up of identical atoms. For instance, you take a brick of gold, you take one gold atom, it's completely identical to another gold atom. But if you pick up a mass of silver, then the atoms of silver and the atoms of gold will be different. Primarily, they will have different masses, and this changes the property of the element itself. So those are the basic elements. But Dalton continued and started talking about chemical compounds. That is material made up of a mixture of different elements, such as water. He reasoned that chemical compounds are made of atoms of different elements, and that those different elements are arranged in specific integer ratios. For example, we said water. Water is made out of, we know today that water is made of 2 hydrogen atoms to every 1 oxygen atom. The way we would write that in chemistry today is H2O. 2 hydrogen atoms, 1 oxygen atom combined make the molecule of water. Now, this was a phenomenal discovery a phenomenal hypothesis, because once we have this, now all of a sudden we can describe all the different materials out in nature and how they react with each other. Now, that leads to one last important point in Dalton's atomic theory. That is that atoms are neither created nor destroyed. Those atoms exist. They will never change. They are only rearranged in chemical reactions. For instance, you have, say, wood, which is made of sugar and water. Sugar, water, and then you mix that with oxygen, you burn it, it rearranges all those molecules, and you get carbon dioxide and water as a result as well. The atoms are not created or destroyed, they're just rearranged. Now, Dalton's atomic theory was fundamental and critical for chemistry. We have learned a lot more, and there are certain points that we will address in future chapters that are not correct, but it was a wonderful start. Later on, towards the later end of the 1800s, a man by the name of J.J. Thomson did a number of experiments on cathode rays. These were negatively charged rays of light. Now, he did a lot of these discoveries, and through a lot of these experiments, he discovered that these cathode rays, these negatively charged rays of light, were nothing more than particles, which we called electrons. And we identified these electrons as a fundamental particle, a fundamental part of the atom that John Dalton theorized. He was able to do more experiments to measure the ratio of the charge of an electron to the mass of an electron, but that's as far as he could go. Robert Millikan, a handful of years later, early 1900s, around the same time as Albert Einstein, he studied the charges of an oil droplet, and he exposed the oil droplets in an electric field so that the electric field would push an oil droplet up, gravity would pull the droplet down, and by perfectly balancing these two forces, he was able to actually calculate the charge of individual droplets. Now, he did this many, many times and found that each time he found the charge of a droplet, it was the multiple of one particular number. That particular number turned out to be the charge of one single electron. So this experiment, along with Thomson's result of the ratio of charge to mass, was able to actually give us the charge of an electron as well as the individual mass of an electron. So here on the right, you see this Q over M. This is the ratio that Thomson discovered, the ratio of the charge of one electron to the mass of an electron. And then Millikan was able to actually calculate the charge of one electron, 1.6 times 10 to the minus 19th coulombs. Combine the two results, we can calculate the mass to be 9.11 times 10 to the minus 31st kilograms. Very, very small mass. So we started off with Dalton creating an indivisible particle, which we call the atom. Continued with experiments by Thomson and Millikan, which showed us the existence of an electron, a very, very small mass part of an atom, but had no measurable volume at the time. But if there's a negative charge in an atom, then there has to be a positive charge in the atom as well. So that raised the question, what is the nature of the positive charge inside of an atom? So Thomson reasoned that an atom looks like plum pudding. Now, if you aren't familiar with plum pudding, it's a bread-like dessert with raisins embedded in it. I think that they call this because they were unfortunate enough to not to know about a chocolate chip cookie. I like to think of it more as a chocolate chip cookie model. Either way, it's the same idea. Thomson reasoned that electrons were like a blob of positively charged matter, the bread-like part of a plum pudding, and electrons are like the raisins inside the plum pudding. Or in the chocolate chip cookie idea, the cookie is the positive charge, and there are embedded little negative charges inside. Those would be the chocolate chips. So this was the idea of an atom, one solid mass of positive charge with embedded negative charges.